Hello everyone, my name is Ghadeer Derbas, a doctoral researcher at IAS-7 at Forschungszentrum Jülich and a PhD student at Wuppertal University. My talk will be about the robustness of building design and solar shading control strategies in terms of occupant behavior. My main supervisors are Professor Karsten Voss, the head of building physics and technical building equipment at Wuppertal University, and Dr. Mohsen Shraibi, the head of a division in civil safety research, IAS-7, Forschungszentrum Jülich. The overview of the presentation, there will be an introduction, then research motivation and objectives, research methods, research investigation, the previous experimental research study in 2019, the current experimental study in 2020, in situ monitoring, case study, research outlook, and contact information. During the last decades, there was a worldwide spread towards sustainable development because of energy crisis and climate change. One of the designer's contributions to lower the energy consumption in building is to use the passive design strategies such as super insulation, thermal mass, and shading control strategies, and so on. Despite all these sustainable technologies, energy demand has not decreased. In fact, 40% of the total energy consumptions is imputable to the energy requirements of the building sector. Previous studies proved that occupant behavior had a major influence on the energy consumption's variations in buildings because they tend to act in order to maximize their comfort. Here we can see the cycle of interactions between the occupants and the environment where they work. Usually there is external and internal factors such as indoor environmental parameters and weather conditions that trigger the user actions in association with specific users' requirements such as visual and thermal comfort as well as indoor air quality. As a consequence, occupants interact with different building devices such as windows, blinds, lights, thermostats, fans, and doors. And they act in a stochastic way because they don't have the same behavior and not deterministically. And these adjustments impact the energy use of building. There is a lack of consideration of stochastic occupant behavior in the energy performance predictions, and this is lead to suboptimal design decision making, which cause big discrepancies and a performance gap between the predicted energy and the real energy consumption in buildings. Here, through this diagram, one of the way to decrease these discrepancies is designing robust buildings. Robust buildings is buildings whose performance show little variations when using different occupant behavior patterns. Through this diagram, we can see the difference between using the standard approach, deterministic approach, and the behavioral approach during the design process. In the standard approach, the designers assume that all people behave in the same way, and at the end we end up with the big performance gap between the predicted and the real energy consumption in building, while in the behavioral approach, designers consider the different behaviors, attitudes, and preferences of occupants, and they use stochastic behavior models in the energy simulation, and this is decrease the differences between the predicted and real energy consumption. The focus of the research is the occupant behavior in office buildings because they consume more electricity due to the intensive use of HVAC system and equipment. And designers tend to design fully automated energy systems in the building, such as smart and intelligent building. One of these systems is the automated shading system, which considered as a promising solution to improve the indoor thermal and visual conditions, as well as saving energy for cooling in office buildings. Unfortunately, previous studies proved that there is a conflict between the expectations from the design phase of shading control strategies, as designers tend to use perfect controllers, and what occupants accepted and preferred. And this conflict leads that occupants frequently override or disable the automated shading system in buildings, either indicating discomfort or implying their desire for customized indoor environment. So there is a need for further research to find the optimal set points to activate solar shading system and to obtain more robust control strategies with limited overall actions by occupants. The research had 4 main methods. The first was a research investigation using a survey in 19 case study. Then an experimental field study has been conducted in a full-scale test laboratory. Then the statistical analysis of in-situ monitoring data in a real office buildings, and finally energy performance simulation using EDI software. It's a software for energy simulation predictions. First, the researcher did an investigation in 19 case study about the configuration of automated shading system, and they used thresholds and set points to activate these systems. Some of these case studies are office buildings and educational buildings in the center. In the right graphs, we can see the most frequent shade lowering thresholds of brightness. 35, it was 35 and 50 kilolux, and in the upper diagram we can see the most frequent shade raising thresholds of brightness, which was 15 and 30. These thresholds were evaluated in the experimental field study. The current experimental study hypothesis was occupants may behave different due to different performance of commercial solar shading control strategies or because of different preferences and perceptions. So there was 2 main aims of the study. First is to investigate the accuracy and the quality of commercial shading control devices, and the second aim was to evaluate the performance of solar shading control strategies in terms of user behavior, thermal and visual comfort. The experiment has been conducted in a full-scale test laboratory in Wuppertal University during the cooling season last year. 31 participants took part in the experiment. There were employees or students working at the center or at the university. Both objective and subjective measurements has been collected from the field study. The objective measurements included shading deployment and user shade interactions, environmental environmental parameters, and weather data parameters. The subjective measurements and was a self-reported web-based questionnaire from the participant. Several sensors and devices has been installed in the test facility. Here we can see the plan view of the test facility with the reference for these devices and sensors that has been installed, such as data acquisition, brightness sensors inside the room, weather stations at the top of the roof, and also the control panels of these devices. The experiment had 4 main sessions. The first session was fully automated without the interfere of the user, and the second and third session was conventional and simple algorithm based on a brightness threshold to lower and raise the shade. And the last session was a proposed algorithm based on 3 criteria: indoor temperature, vertical luminance at the eye level, and solar radiation on the facade. The 3 last session, the users has the possibility to override the system. The first, as I said, the first aim was to investigate the accuracy and the quality of 2 commercial devices, Olexa and Varima. In order to ensure the same condition, both devices are mounted in the same high position with the same orientation, and they had the same solar shading control setting. As we can see from the diagram, that the solar shade lowering events controlled by Zolexa in yellow line, and the solar shading lowering events controlled by Varima in blue, in the same reference day, both devices were behaving differently. In order to examine their accuracy, the control actions of both devices were compared to 3 scientific reference instruments, as well as programmed simulation control algorithm. As we can see from the graph, the first graph here shows the shading lowering events controlled by Varima, The second one, the shedding lowering events controlled by Zolexa, and the last one is the shedding lowering events controlled by the programmed simulation algorithm. It's the most accurate, as all the shedding lowering events is when the brightness exceeded 300 watt per meter square. So it is concluded that both devices were behaving in a different way from the control algorithm and from the measurements of scientific reference instruments, and these properties should be considered in the development and design of automated shading system. The second aim was to evaluate the performance of different solar shading control strategies in terms of three factors: user behavior, thermal comfort, and visual comfort, in order to find the optimal set points with limited overall actions. Mean shade occlusion is the average fraction when shaded are closed. Here we can see there was 5 blind positions were used in the analysis. 0 means fully open, 100 means fully closed, with also 2 slats position of the blinds. 2 metrics were used to evaluate the user behavior, the mean shade occlusion, and the frequency of shade adjustment. As we can see here from the graph that the mean shade occlusion, there was a slight differences in the mean shade occlusion in the last 3 sessions, while the frequency of shade adjustment was less in the last session. It was 33, while it was around 50 in session 2 and 3. This means that the proposed algorithm is the most robust control strategies. 2 PMV, predicted mean vote, and standard effective temperature indices were used to assess the thermal comfort conditions also through the 4 sessions. Also, it can be indicated from the graphs that there was also slight differences in the PMV and AMV, predicted mean vote and actual mean vote, during the 4 sessions, all the sessions were within the thermal comfort criteria. Last, daylight comfort and DGPS, simplified daylight glare probability, to assess the glare and visual discomfort during the 4 sessions were used. There was also no significant difference between the sessions in light abundant and even in the DGPS and GSV glare sensation vote through the 4 sessions. The non-significant differences between the conventional algorithm in session 2 and 3 and the proposed algorithm is due to the limited accuracy and equality of the commercial shading control devices, because the sessions were based on the set point, and these set points was not accurate because of the non-accuracy of these commercial shading control devices. So the experiment will be done again this year, and it's already started in the 7th of July and it will last until the end of October. The new experiment, the new proposal for the experiment, that the shading control will be based on the programmed control algorithm, which is more accurate, instead of using the commercial shading devices Varima and Zolexa. Also, the number of participants was 31 instead of 43, because it's hard to collect more volunteers. The new experiment had 3 main parameters to study their impact on the user-shade interactions. 2 solar shading control strategies were evaluated: symbol with multi-objective control strategies. 2 window-to-wall ratio size were evaluated, and naturally with air-conditioned space were evaluated. Here we can see the new proposal for the new experiment. The experiment will be run for 2 days for each participant. In the first day, the window-to-wall ratio will be 75% with the 3 main sessions, and the second day the half of the window will be blocked to study the impact on the user behavior, also with 3 main sessions. We can see at the bottom of the slide the time schedule of the experiment during the day. It starts at 9 and at 15. Almost 15 p.m. As a normal working day. The last project is the situ monitoring case study. It's an office building occupied since 2017. And the main objective of the case study is to understand the user interactions with automated shading system in real office buildings and to compare it with the user interaction in laboratories, as I did in the experimental field study. And also to driving occupant-centric rules for a shade optimal design and testing the robustness of the buildings in terms of the user behavior by characterizing a model using logistic regression models and study their impact on energy consumption of building and use different parametric design in order to, with alternating the same occupant behavior patterns and see how this impact the energy consumption of the building at the end. The research outlook is to finalize the current experimental study. It will end at the end of October. Data analysis of the new experiment, Luxembourg building statistical analysis and the simulation analysis based on the statistical analysis of the case study. And that's everything. Thank you very much.